Hello everyone and welcome back to the lecture series of learning theory of automata and formal languages. My name is Binayak Parashar. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So, we have been continuing with this lecture series and this is the 5th lecture, and in the past lectures we have seen the basic introductions to automata theory. We have seen the basic terminologies like alphabets, strings, languages, powers, then length, and based on that we have tried to analyze the concept of finite automata, and we have also tried to learn almost 10 to 11 examples on how to design the concept of deterministic finite automata. And based on that we will be continuing with our lecture, and let us check it out that what is our today's agenda. So, today's agenda is we are going to learn about non-deterministic finite automata, in short form it is NFA, and also we will try to look into the concept of equivalence of DFA and NFA. Okay, so, this is the basic topics that we are going to cover up. We will try to design NFA and then we will try to look into the equivalence property of DFA and NFA. Okay. So, somebody other we will try to look into the concept of like no restriction part on the concept of finite automata. Till now we have seen certain restrictions that we are having in finite automata, which is named as deterministic finite automata, but in here we will not go with the restrictions part, we will just go on accepting the language, that is it. Okay. So, let us check it out. So, what is the basic basic preliminary terminologies that we are having regarding non-deterministic finite automata is that first point is that the transition from a state can be to a multiple next states. So, this point is only the most important point to understand in the case of NFA. Let us check a little bit of difference between DFA and NFA, then it will be much clear to you all. Okay. So, let us take suppose I am having a state and I am having one more state, and let us suppose this is the final state. Okay. I am not naming the nomenclature of these states, just I am designate this particular two states we are having. Okay. One is your let me say that this is an initial state suppose, okay, and I am concentrating only one input symbol, say A. Okay. For this input symbol A, this particular state will have a transition to this particular final state. Okay. Or it may be like this, okay, or it may be like this. This particular initial state I have made as a final state, and I have done a transition of A, or you can say a loop of A onto this onto itself. Okay. Now, if we look in these two scenarios, we are having exactly one transitions which is going from one state to another state or to itself, which is the definition of what? DFA. That means you can say one to one you can you can understand in a better way. Like suppose if I want to omit this particular concept and I want to do one to many concept, that means for a single input alphabet I can do not one to one, I can do one to many. Okay. So, that concept belongs to NFA. Okay. So, if I erase this particular thing, okay, and if I write simply a state Q naught, say suppose, and I am having a state suppose Q1, I am having a Q2, I am having a Q3, okay, and in all these states I am having 1 transitions each, and also I am having a self loop, and in all these transitions I am having an input symbol A. So, this can be possible only in the case of NFA, one to many transitions can be done. Okay. What is the main concept of NFA is that it is required only to accept the language. It does not have any kind of restriction that for only a single input alphabet or whatever input alphabet is there will be exactly one transition, not more than that, not less than that. Okay. That is not present in the case of NFA. I hope you have understood the concept of DFA and NFA difference. Now, let us move into the second point, non-deterministic automaton. Yes, as I have already told it is not determined that there should be exactly one transition. So, the name comes non-determinism or non-deterministic automaton. Then NDFA permits empty string transitions. See, as there is no restriction, so NDFA or NFA both are same, can have empty transitions also, like this. Suppose I am having one more state, say suppose QF, and I can have an empty transition, okay, an empty transition. This means that there is nothing string between Q0 and QF, but yes, I can have a string which is having length equals to 0. So, that is known as empty. Okay. So, this is the basic terminologies about NFA. Let us go to the definition of NFA, formal description of NFA. If you have understood in the previous video, we have discussed about the formal description of DFA, we have discussed about formal description of FA also, finite automata, exactly same, only the difference lies here, that is the transition function. Okay. Now, as you have seen into the previous slide says that from one transition, from one state, it can have multiple transitions. That means, how I can write down? I can write down that the total number of states involved should be correspond to the number of input alphabets. So, here I am concentrating only A, it may be A, it may be B, it may be many alphabets, right, and it should go to not a single state, it should go to 2 to the power q, okay, 2 to the power q, got it. So, this is what the meaning, 2 to the power q means it is not a single state, it can go to n number of states. Okay. Now, if you look into the transition function says the same, that q correspond to the number of input alphabets, it will go to 2 to the power q number of states. Okay. So, this is the general difference between the formal description of DFA and NFA. Rest are everything is same. It is a finite number of states, finite number of input alphabets, initial state, final state. Okay. So, now let us go to the next concept. The next concepts is asked about the graphical representation of NFA. Okay. Graphical representation of NFA. So, if we have understood in the previous example, in the previous lecture video where we have understood the graphical representation of DFA, it is exactly the same, no changes are there. Okay. Only one change is there, that I have already told you, is empty transitions are there. Okay. So, let us go into the upcoming slide. Here we will start off with like discussing the numerical part. So, we have taken almost the same language which we have discussed in the previous video while designing the construction of DFA. The same examples we will take, and we will try to look into the difference between that, because to my point of view, if you have understood DFA and if you have practiced almost 30 questions, then there is no not required for you to practice for NFA also. Okay. So, let us check it out, few questions. So, construct a, okay fine, this is not a DFA, this is NFA. Okay. Construct an NFA over given alphabets, so we are having A and B, okay, where the length is equals to 2. Length is equals to 2, you can, if you have not seen my previous video, then please look into the previous video. We have discussed about the length and how to calculate the language for the same. Okay. So, therefore, I am summing up and we got the language as this one, L is equals to AB, BA, BB. Okay. Now, what we need to construct? We need to design a finite automata in such a way that all the strings gets accepted, which is the concept of NFA. So, what I will do? I will take an initial state, say suppose A, I will take one more state, say suppose B, and I will take one more state, say suppose C. Okay. First, I will check for this string. So, first one is what? A, done. Second element is what? A. So, A, finally, it is accepted. Okay. Always remember this A means A dot A. Okay. We will discuss this concept in unit number 2 while we will discuss about regular expression. Okay. But as of now, when we are having two alphabets together, that means it is deviated by through states. Okay. You cannot put these two concepts, these two alphabets together in the same transition. Okay. So, therefore, we got A, now we can, now this is done, now we will check A, B is not there. So, I will put a B transition over here, which we have discussed in the previous examples also, previous lecture. B A, so B is not present, so I can do a B transition from the initial state. So, B A is done, this is also accepted. If I look into B B, it is present. Now, if I check it out over here, everything is done, all the strings gets accepted and we have drawn the finite automata, and this is your required NFA. So, there is no restriction, we have tried to follow the acceptance of the strings which is being done. So, we can stop here and we can describe that this is the final automata, or which we can say final NFA for the given language. Okay. So, if you have if you are drawing a DFA, then we would have required one more transition, because C does not have any kind of transition for both the input symbols, correct. So, I have to draw a like one more transition if we have gone for DFA, correct. But here we are designing an NFA, we are done with the language part, we have the language, all the strings have been accepted. So, we can stop here, and this is the final diagram, clear. Let us go with the next question. Okay, let me first delete this, and I have shown you the graphical part. So, the graphical part will look like this: A will come, then one more state B, then one A single A transition we will got it, then one more state I will take, that is C, which I have made as a final state, and then A. Then similarly, A for AB I will take one this one B transition, for BA I will take one more transition, and for BB I will take one more transition. So, that means overall I got A B A B, okay, which I take A means A, AB means A B, then BA means B A, then BB means B B. Okay, we got all the transitions done. Got it. Next comes the next question. Okay, example number 2. It says design a finite automata that accepts strings containing 0 1 0 as a substring. Now, let us take the language first. In the language, if we look into it properly, then what is the preliminary string that you can have it? It says that, now please don't try to focus on this particular first part, because it is asking design a finite automata. Finite automata can be NFA, can be DFA. So, you can make any one of them, but as of now we are discussing about NFA only. So, we will try to look into the NFA concept only. Okay. Now, it says design a finite automata that accepts strings containing 0 1 0 as a substring. Okay. Now, if we have to look into this, then what is the initial string that we need to take it? Initial string will be 0 1 0, correct. It says that for every string which is present in the language, a substring should be present which is nothing but 0 1 0 always. So, that means if we take 0 1 0 as a substring of that particular language, this is also accepted by the language, correct. Now, if we talk about any more further language, suppose 0 1 0 I have taken, earlier it can be 2 zeros, later on it can be 2 ones, it is possible, right. I need to check that whether 0 1 0 is present as a substring or not in every strings, correct. I can take like this 1 1 1 1 1, then 0 1 0 0, yes, it is present. It can be like 1 0 1 0 0 1 0 0 0, yes, 0 1 0 is present. Okay. So, you need to check that whether containing 0 1 0 as a substring is present or not. So, it will keep on going till infinite. So, I got some way the other few strings. In your examination, you try to put at least 10 to 15 strings, so that you can analyze the particular language, and you can put down, or you can draw the, or you can design the particular diagram, clear. So, let us check the diagrammatic part of it. So, I need to take first of all, always if you are having questions like this where there is a part of a restriction, you try to design that restriction part first. Okay. That means 0 1 0 is the restriction part. So, I will try to design this 0 1 0 at first, and then I will try to analyze what and all left part we are having. Okay. So, I will try to design the first initial part, that is 0 1 0. So, I am having 0, I am having 1, I am having 0, and this will be reached to the what? Final state. So, I have taken this as the final state, this is suppose C, these are the names of the states. Okay. So, 0 1 0 is accepted. Now, some or the other I am satisfied that yes, my restriction part is been done. I need to focus on my remaining maximum number of possible strings. So, you can like think of it, you can like pause the video and you can think of it, that can we start over here with either 0 or 1? Yes, I can start, right, because 0 1 0 before that it can have n number of possible combinations of 0 and 1, right. So, that is why I have taken a self loop at the initial state. Okay. Thereafter, it will have 0 1 0, I will not put anything between them, let it be together. Okay. We cannot separate them. So, next what I can do, can I take a self loop over here in order to like have a n number of possible combinations of 0 and 1 over here? Yes, I can take it, got it. So, that I can have maximum possible combinations. Now, if we can analyze properly, starting with 0 and 1 possible combinations, it can have any number, followed by 0 1 0, it needs to reach to the final state in order to accept the string, right. So, 0 1 0 will be reached to the final state, we are done. possibly we might have after 0 1 0 we might have 0 and 1 possible combinations, right. So, I have taken a self loop over here. So, this is the final diagram of the NFA. Why I have declared that this is a final? Because I am done with the language part and I can disclose that yes, everything has been done. Okay. Now, if we look into this concept, we have mentioned here example of transition table for NFA. So, I have designed an you have in the previous video we have seen about how to design a transition table. The same way you are going to design a transition table over here. How to do that? Simply, okay, in the columns we will be having the inputs, that is 0 and 1, okay, that is nothing but inputs, and in the rows we will be having the states. So, how many states we are having? We are having A as the initial state, B, C, and one more is there F. So, F being the final state. So, these are the states we are having. Now, you just need to compare the transitions. A on sync 0, it is going to C. Now, A on sync 0, it is going to A as well as B. So, I will take like this A comma B. This is very important to understand. Okay. A on sync 1, where it is going to itself. So, I will take A. B on sync 0, B on sync 0, anywhere, any transitions? No transitions, that means it will be phi. B on sync 1, it is going to state C. C on sync 0, it is going to capital letter F. C on sync 1, is there any transition going out from C? No transition, that means it will be phi. Then F on sync 0 and 1, it is going to itself, so it will be FF. So, this is the transition table for the given NFA. Got it? So, I am done with this example. I hope it is clear to everyone. Let us go with the third question. Third question also is very similar. We have done this question in the previous video. So, you can refer to that video. The diagram was similar. I have mentioned previous time also the diagram was similar. It was like this. Multiples of 3 means what? The language will comprise length 3, then length 6, then length 9, and it will keep on going, right. So, the diagram was like this, if you remember, if you have practiced the DFA question. So, A and B, right. So, A okay, 3 times A, then if I get 6 times A, then I will be getting over here. So, everywhere I can give A comma B, A comma B, A comma B. So, if you look into this diagram, it will be having lengths 3, 6, 9, then 12, then 15, 18, and it will keep on going. It will take all the multiples of 3 as well as divisible by 3 as well. Okay. So, you try to practice this question. Now, if you look into this question, we are done with the language part, and if you look into the scenario, it is also DFA, it is also NFA. Okay. You can if you have understood both the videos, then you will be able to understand this concept also. Now, let us go with the next question. Next question says that design a finite automata with the input symbol accept those strings which starts with 1 and ends with 0. So, my language will be what? Starts with 1 and ends with 0. So, the preliminary string, the basic string will be what? 1 0, right? Starts with 1, ends with 0. Try to design this first. A 1 0. Okay. So, I got this particular diagram where starting with 1 and ending with 0, clear. Now, if we look into this scenario, can 1 and 0 in between that you can have n possible number of strings? Yes. So, what I can do, I can take a self loop and I can give 1 comma 0. It is an NFA, we does not have any kind of restriction. So, you can put anywhere or just need to just satisfy the language. So, 1 0 is done. Now, anything we can do it in order to satisfy. If you want, you can also put over here as 0. So, this will what? Starting with 1, ending with 0. Somewhere the other 0 will end on the final state only. Now, if you want to give here starting as 1, you can give it. It is completely dependent on you. If you does not give to these scenarios also it will not hamper your diagram. Why? Because it will start with 1, it will end with 0, and somewhere the other in between that all possible combinations of 1 0 are possible, correct, entirely infinite all possible combinations. So, why to use one more loop over here and one more loop over here? It will not be an like an optimized diagram, right. So, somewhere the other you can remove these two loops if you want. So, this is all about your the example number 4. I have also drawn over here the diagram. Okay. Now, if you get back to the diagram, you can check it out. Okay. Now, come to the last topic of today's session, that is the equivalence of DFA and NFA. Now, if we talk about this particular topic, till now we have seen NFA, we have seen DFA. Now, we might have a question that as NFA and DFA both are same finite automata, having some sort of restrictions between both of them, can they accept the same language? Yes, they can accept the same language because they belong to the same domain. Okay. Whatever language is being accepted by NFA will be accepted by DFA. So, this is a very important point, keep in mind. So, if we look into the expressive power of both NFAs and DFA, we will understood this particular topic. See, first point says that is there a language that is recognized by DFA but not by NFA? No, all languages which is accepted by DFA as well as it will be accepted by NFA also. If you look into the second point says the same concept, that is recognized by NFA but not recognized by DFA, it is not possible. So, this is also no. So, therefore, a language L is recognized by DFA if and only if there is an NFA such that the language of NFA should be equals to the language of DFA, which is the basic like you can say abstract of this particular topic. So, if a language accepted by DFA, it will be accepted by NFA. So, that is what the summary of this particular topic. Now, we need to first focus on this particular point, that the question comes that when we will discuss about the equivalence of DFA and NFA, is it possible that we can convert NFA to DFA, or is it possible to convert a DFA to NFA? Okay. Now, before that I have asked you in the previous video that whether all NFAs are DFA or whether all DFAs are NFA. So, you might have got this answer, but I will not sum up this answer until we finish it up with this particular topic. So, in the next video I will discuss with you all, but let us go with the question part and let us check how to convert a NFA to a DFA. Later on I will tell you why we cannot convert a DFA to NFA, or why like some problem is there with it. We will discuss in the next video, but let us check how to convert a NFA to a DFA. Now, the given question is this one, that what construct an equivalent DFA from the following transition table. How did I got to know that this is an NFA? Because for input symbol B, it is having multiple states for this input symbol. Okay, for the state B, for the input symbol 0, it is having multiple state transitions. So, that means it is not possible that it is a DFA. Apart from that, is there any kind of one more state is there. Okay, apart from that, if you find phi also, then also it will be, you will be able to know that is an NFA diagram. Okay, how to draw this? We need to take a transition table for this. Okay, 0 and 1. Okay. I will let you know the final steps, but how to do it right now. This is what? This is the transition table for NFA. Okay, and this is what? This is the transition table for DFA. Okay, so first step is that you need to convert this transition table of NFA to transition table of DFA. How to do that? Please listen very carefully. The NFA transition table, in the first row, whatever is there, write down exactly over here. So, what it will be? A, B. Now, if we look into this particular row, for which state you are looking into this diagram? You are looking for the state A. So, now you need to scan this row and you need to check, is there any new state apart from A? Yes, we got B. So, bring this B to the next row. Clear? So, now I will be checking for B. If you look into B transition, in the B transition I am having what? I am having BC on sync 0 and B on sync 1. So, write down as it is. So, BC and B. Now, look into the second row. In the second row, while we are checking for the state B, is there any new state that is coming? Yes, a new state it is coming, that is your BC. Now, you might be having a question that B and C are two different states. So, why we are taking as a singleton state? Yes, we need to combine whenever we are looking for B and going for 0 and it is going for B and C state both. So, together we have to take as a single state. Clear? So, now we need to bring this state over here B and C, and we need to check how we need to check this. Now, look into the transition table of NFA. On sync B and C together, on sync 0 it is going to where? B, comma C and C. So, C and C are same, so B C. So, therefore, it will be B and C. You can rewind the play and you can just like revise this topic. See, again I will check for input symbol 1 on seeing B and C, it is going to where? B and BC. B and B are same, so it will be BC. Therefore, is there any new state in the last column, last row? No. Once you are done with finding all the new state, okay, like you are not getting any new state, then you have to stop here and that will be the final transition table for the DFA. So, therefore, if you look into this particular table, which will be the final state? This one. Why? Because C was the final state and now C is merged with B. So, therefore, BC will be taken as a final state. Clear? So, overall this is the transition table for DFA, and if you want to draw the diagram for this, yes, we can draw it. How to draw it? Okay, we can draw like this. So, I will be having one state as A, initial state, I will be having B as the next state, and I will have BC as the final state. Okay. So, A on seeing 0 where it is going to itself, A on seeing 1 where it is going to B, B on seeing 0 it is going to BC, B on seeing 1 where it is going to itself, BC on seeing 0 and 1 both are going to itself only. So, this is the final diagram of the DFA. Okay. So, if a question comes that construct an equivalent DFA for the given diagram or construct a final, or you can say or construct a DFA from the given diagram. So, first of all, if the diagram is given to you, that is transition diagram is given to you, you need to convert that transition diagram of NFA to transition diagram or transition table of NFA. From that the process is this one, transition table of DFA, then transition diagram of DFA. So, this is the conversion process of NFA to DFA. I hope it is clear to everyone. So, let us look into the next example. The next example says find the equivalent DFA for the following machine. Now, if we do a little bit fast, what will be the table? First, I will try to design the table for the NFA, okay, 0 and 1. Okay. Now, if we look into the states, Q 0 is the initial state, okay, then Q 1 and Q 2, Q 2 is the final state. Okay. So, Q 0 on seeing 0 where it is going to itself, Q 0 on seeing 1 it is going to Q 1, okay. Q 1 on seeing 0 it is going to itself and to Q 2. So, it will be what is the answer? Q 1 comma Q 2. Okay. Now, same way Q 1 on seeing 1 it is going to itself and wherever it is going, no, it is not going in, so it will be Q 1. Q 2 on seeing 0 it is coming to itself and anywhere it is going, no, it is going to itself. Then Q 2 on seeing 1 it is coming to itself and going to Q 1. So, therefore, the answer will be Q 2 comma Q 1 or Q 1 comma Q 2, anything. Okay. So, therefore, this is the table that you got, this is the transition table for NFA. Now, you need to convert this transition table to the given DFA. Okay. So, this is how you need to do it. So, after that you just try to do it on your own and you will be getting the answer like this. Okay. So, you will be getting, first you will be having the row as same row as it is. So, Q 0, Q 0, Q 1. Okay. Now, if you look into this particular row, what is the new state that you got? Q 1, bring it over here. Now, let us check for Q 1, Q 1 I got it as Q 1, Q 2 and here it will be Q 1, correct. What is the new state that you have got? Q 1, Q 2. Okay. So, if you look into Q 1 and Q 2, it is coming as Q 1, Q 2, Q 2. So, it will be Q 1, Q 2 only. Okay. And if you look into this one, next one, it will be Q 1, Q 2 only. So, that means the diagram is somewhat similar to the previous one that we have discussed, but I have shown you how to draw it. First, the transition diagram will be given to you. From that, you need to convert this to transition table for NFA, then transition table for DFA, then transition table diagram for DFA. So, this is the way you need to do a equivalence of DFA or NFA to DFA. Okay. So, in the next video, we will come across with one more interesting topic and I will discuss this particular point that I have asked you, that whether all DFAs are NFA or all NFAs are DFA. So, next topic we will discuss about the epsilon transition for NFA. Keep watching these videos. Thank you.